Welcome to our last example video for this chapter for this topic, linear algebra. We are almost done. All we have to do is get through this last video. So let's go ahead and get started. This video is asking us to find the invertible matrix Q such that I can't spell, such that J is equal to Q, inverse of Q, a Q. So this is kind of similar to diagonalization, but of course, this is complex and defective eigenvalues. So I'm guaranteeing you that these examples will have a defective eigenvalue. So let's get started. So the first one, as always, simple, 2 by 2 matrix, characteristic equation. Let's find that boy. If you recall the last example, that this was the same matrix that we looked at. So we know that we can just go ahead and skip this and know that our eigenvalue is equal to 3 with the multiplicity of 2. And we know that our Jordan-Canonical form will be 3, 0, 1, 3. And so to find our Q, well, we just have to find our eigenvalues. Not eigenvalues, eigenvectors. So that's no biggie. We've done this plenty of times, but we've never done it like this before. So when our lambda is equal to 3, we will get 1, negative 2, negative 2, negative 1, 4, 2. This is going to be giving us 0, and this is only going to be giving us one eigenvector, so we don't know what the other eigenvector is. And so here's how we're going to do it. We are going to square this matrix, and this will give us 0, 0, 0, 0, a 0 matrix. Cool. So now what do we have to do is take this matrix, we got to multiply it by some vector, so this is equal to 0. Well, honestly, V2 can be anything. It can't be 0, 0. It can't be 0, 0, because eigenvectors, that can't be true. You cannot have a 0 eigenvector. So it can be 0, 0, but it could be anything else. But there's a condition. Whatever that vector is, this portion here, the original matrix, cannot equal to 0. So a simple one as, and honestly, just please make your life easier. The most obvious one is either 0, 1 or 1, 0. So I'm going to go with 1, 0, and that will be our vector 2. So our vector 1 is going to be the original matrix multiplied by V2. And so this will give us negative 2, 4. And thus giving us our Q invertible matrix being a 2 by 2 matrix, obviously, because we're working with 2 by 2. And it's going to be, so here's what happens. Order matters. So the way you want to align your vectors, even though they're both eigenvalue of 3, the way we align it is from the end of from pretty much, yeah, from the first chain or the first link of the chain to the last one. So our first link will be the V1, our last one will be V2. So this will make this matrix negative 2, 4, 1, 0. So it always goes like that, or like this, however you want to do it. I tend to write it from this way because we find our V2 first, and then we go back to find our very first link, and so that's how you tend to do it. Again, we're gonna do more examples. Hopefully, it'll make much more sense. So the next example is a 3 by 3 matrix. Again, recall from last video, this was the same one as we did in the last lecture, or not lecture, last video. So we know for a fact that our Jordan-Canonical form is already 1, 0, 0, 0, 1, 0, 0, 1, 1. It's 3 by 3, right? Yep. So our eigenvectors value is equal to 1 with the multiplicity equaling to 3. And so, okay, this is new. We have a multiplicity of 3. Eigenvalue is equal to 1. This is the only eigenvalue we have. But what does that mean with our blocks? Like, why do we have 1 by 1 block and then 1 2 by 2 block? Like, is there significant difference? And does the order matter? How do we do this? Well, yes, there is a difference. So what that basically means is that the 1 by 1 block will have its own eigenvector, and then the 2 by 2 block will have 2 of its own eigenvectors. Again, all the eigenvectors have to be linearly independent from each other. So to do this is the best way to do it is obviously to plug in your lambda is equal to 1. But we are going to work with the 2 by 2 block case. So this would be -6, 2, -12, 0, 0, 0, 3, -1, 6. Okay. What we're going to do is we're going to square this matrix, and when we do that, miraculously enough, you get a 0 matrix. And so we have to multiply by some vector v, making sure this is 0, while making sure that the original matrix raised to the first power is not equal to 0. So we can just do the most simple one, which is 1, 0, 0. So that means when you multiply the original matrix by our vector, multiply by v, or I guess v2, we will get -6 to -12. Cool. Now we can divide by 2. It's tempting, but don't do that. Leave it as is. So our q is going to be equal to, because we have our block, our 2 by 2 block here, this will be empty, so this will be -6 to -12, and then 1, 0, 0. And so what about this portion? Well, this portion is fairly simple. Because this is a 1 by 1 block, all we have to do is just find a vector for this original matrix. So for, I'm just going to rewrite it, -2, or -6 to -12, 0 all the way, 3, -1, 6. The eigenvector will simply be 1, 0, 2. And that's our Q, our invertible matrix, and we're done for this example, and we're just onwards to the last one. So this last example, this one's new. This one we have to do everything by hand. But again, it's a 3 by 3 matrix. We have zeros all the way, so honestly we can just use the column of zeros, and we'll see that our eigenvalues are just zeros with the multiplicity equaling to 3. So just the same thing as the last one. So now plug in our lambda is equal to 0, still going to give us the same matrix, and we see just by looking at the matrix alone, we are going to get a rank of 2 and nullity equaling to 1. So that means we will have one 3 by 3 block. So our Jordan-Canonical form will just be 0, 0, 1, 0, 0, 0, 1, 0. So we have our 3 by 3 block here. Our Q, well, that's not so easy to find. So we're just going to plug in our lambda is equal to 0, and which we already did. And so we have to find, because we have to find our missing eigenvector, we have to square this entire matrix. And when we do, we will get not a 0 matrix, because we're going to have a 1 here. And again, so now this time, we want our nullity to be the same as our multiplicity. So our nullity was 1 in the first case. The second case is 2 because we only have this independent one, so the rank is 1. So again, we have to square the, not square, we have to multiply this we have to multiply this matrix again by itself squared. And so when we cube, actually different color, squared. So when we cube the matrix, we will get finally our 0 matrix. So we get to find a vector such that is equal to 0. We can pick anything, but we have to double check that it doesn't zero out the rest of them. So that means when you multiply v3 with this vector, it has to give you our v2 that is not equal to 0. And then when you multiply a by v3, it has to give us our v1, and it cannot equal to 0. So we can, for sure, for fact, second row will have to be 0. And that's all we can really do for the second vector. The first one, however, is we look back at our matrix, have 1 here, so that would just give us 0, 1, can't be 1, 0, 0, because it will make our second vector 0. Okay, there we go. So this is going to be our v3. Our v2, this is going to be equal to 0, yeah, 0, 1, 0. 0, 1, 0, and then our v1, it will just be 1. That part will cancel, and then not 1, 0, 0. And so now we just plug in. Again, we're going from the end link to the first. So this would be 1, 0, 0, 0, 1, 0, and then 1, 0, 1. And that is our answer. Obviously, you can find the inverse matrix, but all we have to find is Q. And that is pretty much it for this video. That's pretty much it for linear algebra. We are done with linear algebra. This is the end of this series, and I look forward to seeing you guys in any other series that you are curious to learn about, or if you need to pass a class, I'll be seeing you there. So other than that, enjoy the rest of your day, enjoy the rest of your semester or summer or whatever you're doing at the moment, and I'll see you guys in the next video.